Hi, everyone. So this lecture is going to be about half-lives of a radioisotope. And we'll talk more about what a half-life is, but half-lives are important for several reasons. And one of the big reasons is radioisotope dating. When we have really old objects like the Dead Sea Scrolls, we can actually use the radioactive isotopes within that sample to calculate how old it is. And so the Dead Sea Scrolls were dated using carbon-14. So it's just a famous example. The learning goal for this lecture is if we're given the half-life of a radioisotope, can we calculate the amount of that radioisotope remaining after one or more half-lives? Let's take a closer look at half-lives. So the half-life of a radioisotope is the time it takes for the radiation level to decrease or decay to 1/2 of the original value. So imagine we had a sample of iodine-131. After a certain amount of time, half of that original sample will have decayed or given off radiation. And so half of it is converted to the new element and half of it's remaining. After another half-life, half of that sample has decayed again. Another half-life, another half of it decays. So imagine if we originally had 20 milligrams of this, after one half-life, we'd only have 10. Another half-life, you'd only have 5 remaining. Another half-life, 2.5 remaining, and so on and so forth. If you were to graph the amount of initial radioisotope versus time, you'd see that the decay is not linear, but it's logarithmic. And so using half-lives is a simpler way to calculate time and the amount remaining. If you notice, these bar graphs are every 8 days, and that's because that's the half-life of iodine-131. So after 8 days, half of our sample is gone. After another 8 days, another half of the sample is gone. Another 8 days, another half, and so on and so forth. And it keeps going. This table shows the half-life of some common radioisotopes, both naturally occurring and medically used radioisotopes. Let's take a look at the naturally occurring ones first. So carbon-14, it's this symbol, has a half-life of 5,730 years, and it's a beta emitter. Potassium-40 has a half-life of 1.3 times 10 to the 9th years. It's a beta and gamma emitter. Radium-226 has a half-life of 1,600 years. It's an alpha emitter. Strontium-90 has a half-life of 38.1 years, also an alpha emitter. Uranium-238 has a half-life of 4.5 billion years. It's an alpha emitter. Now, that's a really long time. So if you have a sample of uranium-238, it will take 4.5 billion years for half of it to decay, which is pretty much the age of the Earth, right? We actually refer to uranium-238 as depleted uranium because it's less radioactive than the other isotope of uranium. And this is what we use in tank armor and armor-piercing ammunitions like tank bullets. The reason why we use depleted uranium is because, one, it's really dense, and so it makes really good armor and armor-piercing rounds. But the other reason is because its half-life is so long, it's not giving off radiation very frequently, right? You can have a uranium, tank round sitting next to you, and because its half-life is so long, it's only spitting off alpha particles, very, very infrequently. And so it's pretty safe to be around, actually. Now, some of these medically used isotopes have much shorter half-lives, right? Chromium-51 has a half-life of 28 days. It's a gamma emitter. Iodine-131, half-life of 8 days. It's also a gamma emitter. Iridium-192, half-life of 74 days, beta and gamma emitter. Iron-59 has a half-life of 44 days, beta and gamma emitter. Radon-222, only 3.8 days. And technetium-99 has a very short half-life of 6 hours. Now, why do we think the medical isotopes have such short half-lives compared to the naturally occurring ones? Well, first of all, the reason the naturally occurring ones have long half-lives is because if they had short half-lives, they wouldn't exist anymore, right? The Earth is 4.5 billion years old, so anything with a short half-life will have already decayed by this point in time. So only things with really long half-lives are still existing. These medical radioisotopes are not necessarily naturally occurring. A lot of these are created in a lab, and they have really short half-lives, which is useful for medicine. In medicine, we want the radiation, right? We either want to kill cancer cells with radiation, or we want to use the radiation for medical imaging. And so we want things that give off radiation frequently so that they're useful, which also makes them more dangerous. So all these medical isotopes typically have short half-lives. Now that we've talked about what a half-life is, let's talk about how to use it in a word problem. So the general guide to using half-lives is as follows. The first step is to state the given and needed quantities. So look at what they give you and then look at what they're asking you for. The second step is to write a plan to calculate the unknown quantity, write the half-life equality and conversion factors, and then set up the problem and calculate the needed quantity. Let's do an example problem together. So this question is telling us the radioisotope strontium-90 has a half-life of 38.1 years. If a sample contains 36 milligrams of strontium-90, how many milligrams will remain after 152.4 years? So let's reread the question and mark down what is given to us. So we know that the half-life is 38.1 years. That's going to be important. So one half-life is equal to 38.1 years. We're going to use this as a conversion factor. They're telling us that our sample is decaying for a total of 152.4 years. Let's figure out how many half-lives that is. 152.4 years. And I'm going to insert a conversion factor from this equality. So we want years to cancel, so I'm going to put years on the bottom, and we want half-lives on the top. And so there's one half-life equal to 38.1 years. When we multiply these, the years will cancel, and we'll have 152.4 divided by 31.8. Punch that into your calculator, and you will get 4 half-lives. That means that our original sample that contained 36 milligrams is going to decay in half 4 times, 4 half-lives, right? So if we cut this amount in half, what's half of 36? 18. So after one half-life, we'll have 18 milligrams. After another half-life, 18 divided by 2 is going to be 9 milligrams. If it decays another half-life, it's going to get cut in half again. So what's half of 9? 4.5. And a fourth half-life decay, it's going to cut that in half again. 2.25 milligrams. And so this is showing that we are decaying our amount in half 4 times, 4 half-lives. Okay. Now, instead of writing all this out, you could actually simplify it mathematically. So if we're cutting the amount in half 4 times, that's the same thing as saying 36 milligrams times 1/2 raised to the 4th power. So if you want to speed things up instead of writing it out every step, you can just punch it into your calculator like this, and you'll get the same answer, 2.25 milligrams. And if we were being really picky, we would round this to two significant figures because that's what's given in the problem as the least accurate measurement. So if we rounded that to 2 sig figs, that would be about 2.3 milligrams. Okay. So take the total time, convert the total time into a number of half-lives, and then take the original starting amount, cut it in half to the power of how many half-lives there are to get your final answer. These next couple slides are just showing us solving it as we did together. So let's double check to make sure we got the right answer at 2.3. They rounded down to 2.2, which is incorrect. It should be 2.3. But looks like we did it right. Let's do another study check. So carbon-14 was used to determine the age of the Dead Sea Scrolls. If the Dead Sea Scrolls were determined to be 2,000 years old and the half-life of carbon-14 is 5,730 years, what fraction of this half-life has passed? So here's the question with some blank space for us to write. So it's asking what fraction of this half-life has passed? So 2,000 years. And we know that the half-life is 5,730 years. So there's one half-life for every 5,730 years. When we multiply this across, the years will cancel. And if we punch that into our calculator, 2,000 divided by 5,730, I get 0.3490401, yada, 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 and it keeps going. Half-lives. Well, looks like technically 2,000 is only one sig fig. So if we were to round this to one significant figure, that would be about 0.3 half-lives. That is the fraction of a half-life that is passed. Next couple slides are just showing this calculation, and it looks like we got it correct. Let's do another problem. The half-life of iodine-123 is 13 hours. How much of a 64 milligram sample of iodine-123 is left after 26 hours? Well, let's start with the total time, 26 hours. And we want to figure out how many half-lives that is. So we're going to insert a conversion factor. And we know that one half-life is 13 hours. That was stated in the problem. So 13 hours on the bottom. When you multiply that across, the hours cancel. And so 26 divided by 13 is 2. That will be 2 half-lives. The initial sample was 64 milligrams. So we are going to cut that in half twice, which should be 16 milligrams. So the other way to think about that, right, is if you had 64 milligrams initially, you're going to cut it in half over 13 hours because that's the half-life. That'll be 32 milligrams. And then another half-life or another 13 hours. And that'll cut in half again to 16 milligrams. And so the total time is 26 hours. And that was 2 half-lives. So final answer, 16 milligrams. And the next 2 slides are just showing us calculating as we did together. And it looks like we got the right answer. Thanks for watching, and I will see you in the next video.